Well, thank you for having me tonight. I haven't been here in several years, and I feel remiss in that, so I need to start getting in here and giving you updates more frequently. Cheryl mentioned that it was going to be a basically one-year update, and instead I'm going to catch you up for the last several years of how many times we've, the things that we've done, what we've accomplished, so that we can kind of give you a good idea what's going on at the treatment plant. So first of all, let's start out with Division 1 treatment plant projects. That was in 2009 that Cheryl mentioned. So we finished that several years ago, made the following changes. We put in inline grinders or preliminary screening. Dry weather pump station was added. Raw sewage bypass elimination, yay. Standby power generation and grit storage pads. Wanted to show you a picture of what these inline grinders do, and they actually grind up everything that comes in. I mean, they're called channel monsters. That's what they're called. And you can see the factory picture on the left and see a dirty picture of one that's being pulled out and cleaned and greased and everything on the right. That's one from the actual treatment plant. We have 3 inline grinders, so all of the raw sewage coming into the plant goes through these grinders before it hits the pumps. Of course, that's to protect the pumps, but it also makes treatment better, and you'll see that in our downstream processes. And our pretty new pump station, our former one that we had was actually in the floodplain, if you can imagine, was over 50 years old, still using the 50-year-old pumps, I might add. So a little past their designated useful life. So we have these nice new pumps. These are called vertical turbine pumps, and they are much more energy efficient than what we typically were using before, which were centrifugal pumps. So we chose that to enhance our project because it was more of an energy savings and a better type pump and made in the USA. Just thought I'd toss that in. And this is one of the things that we were very proud of with this project. That's one of our 4 generators. So these are 1,000 kVA generators to run our utility. Currently, or prior to that point, what we did was we had 2 parallel feeds coming into the plant. So if we lost power on one side, then we would switch over to the other side of feed. And if both lost feed, which happened in the ice storm several years ago, I know everybody remembers that massive, terrible ice storm that we had, then we're dead in the water and we're begging light and power to forget about everybody else and come fix us. So now we don't have to do that. We can switch over to our generator feed. It's got an automatic switch gear in it. If we lose both incoming line feeds, it will automatically switch to generator power that it will operate all of our treatment plant processes. So we do not have to be without anything. So results achieved, new pumps and piping, a grit pad that was out of the floodplain. That was another thing. In wastewater, we have grit, which is sand, coffee grounds, eggshells. And so our grit pad prior to that was next to that old pump station, which was in the floodplain. So the water comes up, you can't put your grit over there. You got to create a place over there that's not appropriate. So when we built, we said this has got to go. It's got to be straightened out. Build a new grit pad that is out of the floodplain, and we don't have to worry about that. And then that great raw sewage bypass point that was eliminated, we were super happy about that. Full facility backup generation, and then a 50-year-old electrical switchgear was replaced. I said something about the parallel feeds that come into the treatment plant. What that is a device that's supposed to automatically throw over. It lost line feed, it's supposed to automatically switch over. It wasn't so automatic anymore. So the operators were trying to switch it over, and it got to the point where our biggest electrician had to stand on it to get it to go into place. So obviously that's just not going to work. You can't have that kind of thing. So I made that a priority. We had to get that electrical fixed, and we did, and so now we have the automatic switchgear to not only do the parallel feeds, but to switch to backup generation. Division 2 treatment plant projects. So we added a new headworks that included parallel fine screens, grit removal equipment. Each side can handle full treatment. At the end of our long-term control plan, we're supposed to handle 54 million gallons per day. Each side of this system will handle 54 million gallons per day. That's how we designed it. That's what we wanted. We added 2 new final clarifiers, 110 foot in diameter, 13 feet deep. These are great. Actually, the flow from 2 of our older clarifiers, the 1938 or the 1960s versions, will fit into one of these. So we basically almost doubled our final clarification capacity. We got additional wet weather treatment and storage, and we updated our holding tanks for sludge. And then our 2 oldest final clarifiers, the 1938 versions, were rehabbed at that time. I am a firm believer in reusing what you've already got. If you've got concrete in the ground and you can rehab it, you reuse it, repurpose it, figure out how to make it work correctly, and that's what we do. And this is our new PTF where those screens are at. When they were building it, they called it the castle because it has so much concrete in it, because it can have hydrogen sulfide buildup if we don't use the appropriate steps, and so they made it very thick, properly treated concrete so it won't degrade. And that's on the right is my lovely 110 foot diameter clarifier. It's made treatment at the plant so much better and us able to handle more wet weather. I'm weird on clarifiers. I like them. They do their job. Very simple devices, and sometimes simple is the best thing when it looks at water treatment. Now to the left, these are fine screens, and you can see that there are actually 2 of them, and they are in parallel, but we can actually turn them both on and run them at the same time, but we don't need to, so we alternate them. Like I said, these will handle up to 54 MGD alone. And in the middle, you'll see the hole that's down in there. That actually is a bypass channel. The reason we felt that was important is because we've got water that's pumping about a mile from the Dewey Street plant. And if something ever stopped up that water, then where's that water going to go? It's going to bypass to the river. To me, that was never an acceptable potential. So we put in this bypass channel completely passive because it may not get through the fine screens, but I won't have to worry about raw sewage going into the river because I didn't think ahead. So that was one thing we insisted that the engineers add. We felt like that was an important thing, and I suspect in all their future diagrams they create that as well. This is a picture of a primary settling basin. I just wanted to put in what one really looks like, or a design from a book. Sludge is accumulated at the bottom and goes out to biosolids for treatment. Skimmings are collected off the top. It actually has a device that rotates. And what we did is, you can see an actual primary clarifier, one of our old ones, in the picture to the right. And we had it drop down for inspection and repair. And this device is being used for wet weather purposes. So, results achieved. The wet weather storage treats approximately 1.37 million gallons before rain can even discharge. Now, the important thing of that we have noticed is if you get that little bitty rain that used to, the little blurb of rain, little bit, we would bypass in the past. Well, now what happens is it fills this tank very slowly, and if the tank isn't full, it does not overflow, and we bleed all that water right back into the treatment plant. So it's doing its job as a holding tank, and so we're happy with the way that's working. The influent wastewater does go through the fine screens, and screenings are washed and compacted before we take them to the landfill now. So by doing that, we've reduced the amount of water, so we're not paying to haul water, plus we're recirculating that water into the treatment plant. And then the additional clarification allows wet weather flows to get better treatment and avoid solids washouts. In the past, what we had is our older clarifiers. We have the flow divided up to where more flow basically can go into the deeper clarifiers, because when at high flows, you could get solids washouts. The solids would get real fluffy and kind of build up. And so now we don't have that because we've got 13 foot to work with instead of 8 feet. So, you know, you get 3 or 4 days of 40, 45, 50 million gallons of water trying to get through this treatment plant, and now we're not losing solids because it's properly set up. Division 3 treatment plant projects. They were supposed to begin design in 2012, but they began in 2012. Supposed to be designed by our consent decree, long-term control plan in 2015. So we actually got started earlier on those. So the new laboratory has been built and is in service. 4 of the 1960s clarifiers were rehabilitated, so that means all 6 of the older final clarifiers have now been rehabbed and rebuilt. So existing equipment. And we have under design conversion of our oldest primary clarifiers into additional aeration treatment units. When we do that, we're like a lot of other cities, we're going to be under a phosphorus mandate. We had 3 years compliance scheduled to get to that. We chose to go biological phosphorus removal. We prefer not to add chemicals if we don't have to. By doing that, what we've done is we've adjusted the treatment plant. We're already getting phosphorus removal at our treatment plant and doing a good job of it. So we're coming close to that 1 milligram per liter now, most of the time. So by repurposing this equipment and designing it properly, we can utilize that, and, you know, once again, we're going to let the bugs do the work, let biology and nature do its work, and instead of a bunch of chemicals in the system. Concrete repairs also planned for the 78-year-old concrete. If you've been to the treatment plant, you've seen we've got some areas, especially the 1938, 1960s area. We got crumbling concrete that needs addressed. I got down into the clarifier and shot up to take this picture. This was a weir in one of our secondary clarifier settling tanks prior to it being replaced and repaired. Laboratory project, you can see the fume hoods. The prior lab had a small fume hood and only one of them. So for safety purposes, it was not that ideal because basically you're standing in line to use the fume hood to get your job done, and we don't want anybody taking shortcuts. So the new lab actually has 4 fume hoods, so you can be working all over the laboratory getting your job done. And then to the right, you can see that we have room to get things done. You're not going to be bumping into anybody, and couldn't tell you the number of times I about ran into somebody in the old lab because it was pretty small and narrow. So results achieved: proper safety equipment for the laboratory, updated clarifier tanks, hopefully going to get another 50 years of service out of them. More treatment process flexibility, as I mentioned. We expect to bid that treatment plant project this year that's going to add the aeration capability and phosphorus removal. And we're going to repurpose the existing equipment and save millions of dollars. Some other results I want to talk about. We've increased the average amount of wastewater flow that we process and the amount that we can take through full treatment. As I noted, we can take a 0.35-inch storm without causing an overflow. And we've added capacity at various areas through pipes and other structures. Want to show this photo because it shows, you can see back in 2012, the blue is influent, the green is effluent. And so back then, our maximum amount to come into the plant was 46 MGD. Maximum effluent was 29 MGD. 2015, I just picked full years. we're able to pull in 56.8 million gallons and process through full treatment 35.3 million gallons. So we've made some big strides, as you can see, because the more that's processed through full treatment and the more that's pulled into the plant means it's getting treatment instead of going straight to the river. And so we've also increased the average amount of flow. And so you can see the average in 2012 for the effluent was 15.4. The average now is closer to 16.8. Collection system projects. We did the sewer cleaning and televising project. We did Division 1 Athletic Park Conveyance project. The Morton Street Storage project was done as well. New lift station predictive maintenance that we're doing that's avoiding us from having any overflows. We're now working with the city engineer so that when we do repairs in the sewers and the storm sewers, we are, instead of trying to put just a patch on something, we're trying to put a long-term repair, make it last. And we've added CSO and lift station metering. So that means every CSO event has a meter. We could go into full panic mode. If we get a CSO alert and it's not raining, you'll see staff scrambling. Now, typically what happens is these have devices that if a mouse runs across it or something, it'll send us an alert, which, you know, we'll take that. We can deal with that as long as, because that means I can send somebody out and check and make sure that there's not a problem, and I don't have a problem out in the collection system that I have no idea about. So that's really critical to us, is that level of knowledge. And then the lift stations, we have 33 lift stations out all over the city and outside of the city. And we actually, right on our phones, we can look and check and make sure every lift station is operating. If a lift station is starting to go down or has a problem, it calls in and it actually goes through a list. So if the operator doesn't catch it, it goes through, it may get Carmen, it may get me, it may get Rick, whomever, and then we make sure that it's addressed. Instead of trying to count on a neighbor who has to listen to a horn or see a light and call in, and you never know how long it's been down. So we didn't feel like that was appropriate, so everything is reporting to us now. So I wanted to show a couple pictures of lift station predictive maintenance that we're doing. That meant we went out and pulled all the pumps and did pump station work. To the left, you can see one of our biggest pumps. That's a 125 horsepower pump being pulled to be checked out. On the right, you can actually see the vac truck in there cleaning out the insides of the lift station so that we can make sure to keep all the capacity that's there. If you get any debris out of there, then you can make sure you've got the full use of your lift station and find problems if they're there. Morton Street Storage Project. That is our 108-inch diameter sewer here in town. And it is, you can see them pulling out that piece of pipe. They actually had to cut the pipe open. What we found out is that we actually had additional room to do storage in this pipe. So we put in 2 weir structures, and to the right is the weir structure. So it goes, dry weather flow goes normally through a little hole in there. And wet weather flow, if it's going to get to the CSO, has to go up over the top of that weir to get out to the CSO. Now, I'll tell you here in a minute how much we get to store in that. Sewer cleaning and televising. All that debris on the ground looks like a piece of wood, a lot of concrete and brick. That was all down in a sewer that was pulled out. So you can imagine how much blockage and how much buildup and possibly getting into homes. And then to the right, you can see one of the hand-laid brick sewers that we have here in town. Some of them are in really remarkably good shape, but back then they made everything, you know, pretty well. But that's an over 100-year-old sewer still in service. Okay, now it takes more rain to activate that Morton Street 108-inch CSO. In 2012, it would take about close to 1.1 inch of rain to activate the CSO, and now it takes over 1.4 inches of rain. So that means that those structures that I talked about, the weirs, are actually holding the sewage in. So collection system results achieved. 34 miles of sewers were cleaned and televised. The athletic park conveyance project, where I showed you the CSO, 500,000 gallons of storage. We eliminated 2 CSO discharge points with that project. The Morton Street Storage Project, 1.1 million gallons of storage that pipe will hold. The Predictive Maintenance Project is panning out, doing a good job for us. We've also lined sewers and manholes to reduce infiltration so you're not treating groundwater. And our lift station monitoring and CSO meters allow us to be more responsive and constantly in touch. So that was actually the 8th Street CSO, and it shows the closed picture. Like I said, one of my favorite photos. When IDEM was doing our permits, they're saying, you didn't happen to take any pictures of that. Oh yeah, let me send that to you. They were just tickled to death that we actually showed the progress. And so we started with 28 CSO points, we're down to 11 now. Sewer repairs, I talked about other things that we're doing. That's a riser that we actually put onto a manhole. And what this does is when the sewer fills up, and we put in a few of these along the river. We've continued to put more in if we find a problem area. If the sewer gets full, it allows it extra room that it can move up into that structure and not get a chance to overflow or back up into a person's home that's adjacent to the river. So this was relatively inexpensive to do that, and you'll see those along the trail where we've added that. And that's something that my collection system foreman came up with. In conclusion, made lots of progress on the CSO long-term control plan, and we've addressed both collection system and treatment plant, and then I've pulled in several other projects that the need to do projects like that switchgear that wasn't addressed in the long-term control plan, because when you're talking to the state and the EPA, they don't know what's in your treatment plan and what you need to plan for. So you have to plan for your own stuff as well. 2 projects currently under design, with the phosphorus removal project that I mentioned to you, and then also the Greens Branch Interceptor sewer. That's a 96-inch diameter sewer, takes in 50% of the flow for the whole city. Segmented clay tile, over 100 years old, and we are going to bid that out probably for a relining, and that will avoid water coming into it, plus give it more structural integrity. And our updates allow us to operate the treatment plant more effectively, produce better water quality. And this is actually at our outfall, and I took a picture of it because I'm like, wow, that looks great. We had an inspection just last week, and our inspector just said, wow, that is really clear. That's what you want to hear. That's what you want to see. And then I crawled down to the outfall so I could get this picture, just clear as a bell. That's what we aim to produce every day at the Anderson Wastewater Treatment Plant.
Hello, good evening. My name is Carmen Davis, City of Anderson, Water Pollution Control Utility. I am the Industrial Surveillance Manager for the pretreatment section. Tonight, my presentation will focus mainly on data that we have collected from the White River. To those of you who don't know me very well, public speaking is not my forte, so please, Cheryl, don't ask me to do this for another couple years. Let's see. I struggled with this presentation a bit because there's so many facets to the White River and my job that I could talk about. Last week, Nara helped me reduce the number of presentation slides from 120 to about 45, so we wouldn't be here all night long. So I really tried to focus on my audience. Everyone here has been on a cleanup. That's why you're here. It didn't make sense, really, to discuss all the reasons why somebody shouldn't pollute. Y'all know that. It didn't make sense to even talk about how pollution gets in the river. You know that. Or even what pollutants can be found in the river. You know those two really. Because most of the people in here don't pollute and already have a good understanding. So I will stick to what I know and what I've seen. First off, I'd like to give you a little bit more information, kind of in complement to what Nara has said about the plant and about the best department there is, pretreatment. The Water Pollution Control Utility is a 21.25 million gallon activated sludge wastewater treatment facility with primary clarification, primary fine screens, grit removal, fine bubble diffuser aeration, secondary clarification, tertiary nitrification biotowers, multimedia filters, and chlorination dechlorination facilities. Plant design peak flow is 40 million gallons per day, which is different from what she said for the PTF, because that one building can hold the 54. We can reach peak flow during heavy rain events, but on a typical day, our flow is about 15 million gallons per day. The treatment plant services the citizens of Anderson, our industrial facilities, and also the town of Edgewood. And of course, the treatment plant discharges into the West Fork of the White River. And she hasn't seen this picture yet. Well, the plant requires many different departments in order for it to operate properly. We have management administration, IT, plant operators, maintenance personnel, biosolids personnel, sewer department personnel. They take care of the collection system mainly. Electricians, relief and utility, laboratory, and pretreatment personnel. And really, Nara is the glue that holds us all together. The pretreatment department is normally staffed by 3 employees. And the department itself, my job, it really covers a wide range of functions in the community and at the plant. We take care of industrial inspection and monitoring, sampling events, and also compliance and permitting. We take care of groundwater remediation, monitoring, sampling, and compliance, community outreach, spill responses, river sampling and monitoring, data collection and analysis. We look for trends, setting local limits, collection system investigation. If there's a problem in the sewer system, sometimes we may need to go out and check things out. Also, fog reduction with inspection and sampling. And we also try to prevent sanitary sewer overflows by going to different restaurants and making sure they're not putting in too much grease. We also report compliance to state and federal regulatory officials. Now, the term pretreatment means the treatment of wastewater by commercial and industrial facilities to remove harmful pollutants before being discharged to the sewer system. The objectives of the pretreatment program are that by placing control or limits on certain levels of pollutants in wastewater discharged to the sewer system, you can prevent interference with the operation of the treatment plant or prevent the introduction of pollutants that would pass through the treatment plant going right to the river. You also improve the opportunities to reuse and recycle wastewater and sludge. And then you also prevent the introduction of pollutants that could cause health or safety problems to the river, or to the public, or in the river. And none of this would be possible without the Clean Water Act, which was introduced in passed in 1972. Since then, since the general pretreatment regulations were also passed in 1983, the National Pretreatment Program has made great strides in reducing the introduction of toxic pollutants to the sewer systems and the waters of the United States. I really could go on and on about pretreatment. It's, in my opinion, one of the best jobs in the city because I get to do all of those things, and it's never a dull moment. It's something new almost every day. But one of the highlights is river sampling. And we get to collect samples up and down the White River before and after the plant, all year round and in every kind of weather. In the winter, frequently we have frozen rope and temperatures too cold for our probes to register. I was there that day. Currently, we are collecting sites from 8 different locations. We're collecting samples from 8 different locations. We start out at 500 East Bridge, then we go to the Range Line Road Bridge, Pittsford Ditch, Truman Bridge, the Grand Avenue Bridge over Kilbuck Creek, Madison Street Bridge, Veterans Bridge, and then also State Road 13 Bridge by Perkinsville. Now, by doing it in that order, we're proposing to follow the flow through the city of Anderson. Now, the waters that we test, or while testing the waters that we collect, we test for many different things. When we're out collecting samples, the first tests that we do are pH and dissolved oxygen. We test those right off the truck in the field. And the rest are analyzed in our laboratory for coliform bacteria, E. coli, BOD, total suspended solids, total dissolved solids, phosphorus, metals analysis, hardness. We also do biomonitoring testing biannually to determine aquatic toxicity in wastewater effluent. Dissolved oxygen is the amount of oxygen dissolved in water that is available to sustain aquatic life. DO is the most important indicator of the health of a water body and its capacity to support a balanced aquatic ecosystem of plants and animals. I know this next slide is very busy, but dissolved oxygen is inversely proportional to temperature. As temperature goes down in the winter, the DO goes up. As temperature goes up in the summer, DO goes down. And I believe the next slide shows this data trend over about 6 years. Through seasonal changes, we tend to stay right in that favorable range. On really dry seasons, like in the summer when we're in a drought, we tend to go a little bit in the uncomfortable zone. So we also test bacteria. Let's see. E. coli is one of the most common species of coliform bacteria. It is a common component in the large intestines of humans and other warm-bodied animals. It is found in high numbers in human sewage. So we kind of consider E. coli to be an indicator organism because it's easily cultured and the presence in water indicates that there is some sewage in there. And these are some of the readings. The peaks were probably taken during a wet river, a CSO event. Biological oxygen demand is the amount of dissolved oxygen used by microorganisms as they consume organic matter. So the more organic matter there is in water, such as sewage or even pollution, the greater the BOD, so the higher the BOD. But that also inversely affects the dissolved oxygen because then the dissolved oxygen will lower. So BOD is a reliable gauge of organic pollution in a body of water. And it's one of the main reasons why we treat wastewater prior to discharge is to lower its BOD. The next slide shows we pretty much stay low. The peaks are wet weather events. And this slide shows the inverse proportion, or the inverse relationship. The red line is BOD, the blue line is dissolved oxygen. As BOD gets higher, dissolved oxygen gets lower until eventually it levels out. Another element of water testing that we do is with metals. The city tests for cadmium, chromium, lead, zinc, and copper. We also have the ability to test for silver, molybdenum. We don't really. and mercury, of course. Heavy metals can enter a water supply by industrial and consumer wastes, or even from acidic rain breaking down soil. Metals are dangerous because they tend to bioaccumulate. Bioaccumulate, and this is the technical version, it means to increase the concentration of a chemical in a biological organism over time compared to the concentration in the environment. Compounds tend to accumulate in living things when they're taken up quicker than they're released. They're excreted. The next graphs, and this is an example of bioaccumulation. As metals sink to the bottom in the sediment, microinvertebrates take up the metals, and then of course they're eaten by minnows, which are then eaten by larger fish. It's the chain of life. Now, I want you to tell you the next graphs, and there's going to be a series of 5 or 6, they reflect data collected from the White River over a 6-year period of time. I just wanted to note that all of the spikes in the graphs, except for one, are under acute and chronic water toxicity limits. So even though we have spikes, these are well under limits. We have chromium. Cadmium was the first one. This is chromium. And if you'll see that this purple spike here was taken at the Madison Street Bridge, and that's before treatment. And I honestly think that spike there is from that Delaware Street influx where that landfill was. We got copper, nickel, lead. We have one zinc spike there. That one zinc is a little bit over chronic and acute toxicity, but that spike does not reflect at the plant. That's also one of the ones that were right at the Madison Street Bridge that I think is leachate from the landfill. Acute versus chronic toxicity. This is just an example of the limits that are set here. Now we got mercury and PCB. Testing indicates there are not high levels of mercury being discharged in the White River from the city of Anderson. PCBs, though, still can be found in the sediment. Mercury testing is conducted at Water Pollution Control on a quarterly basis. It is not a sample collection method that is easily done on a river boat, without a boat. We would need a boat, but you'd also have to use a clean hand technique. And even somebody's breath can affect the sensitivity of that test. Now, PCBs, polychlorinated biphenyls, are tested frequently at the plant from our sludge and grit collection chambers. PCBs are mainly detected in sediment, and the city does not have a history for collecting PCB data information from the river. It's also one of those tests that you kind of need a boat in order to get a good collection. A little bit about the two. PCBs are organic chemicals manufactured by humans, insulating electrical parts, caulking, lubricating machine parts, paints, but they were banned back in the 1980s. And occasionally we still get influx from heavy rain events moving sediment throughout the collection system. Now, mercury is a heavy metal that can come from both sources, man-made and natural. These sources include factory outputs, leaching from landfills, and strangely enough, dentist offices. In the environment, mercury can be converted to methylmercury from bacterial interactions, and that methylmercury is taken up by microinvertebrates, kind of like a bioaccumulation with metals. The last slide in this section is about excessive nutrients. Now, we don't see too much algae in the White River. It just seems to be running too fast, and there's a lot of oxygen. But the city does testing for ammonia, nitrogen, and phosphorus levels. I've just started taking samples from the river for phosphorus, but we have been collecting samples from the city of Anderson for a little over a year. The phosphorus data I have is we're having, from what I found off the river, it's less than a 1.0 milligrams per liter. I think the highest was a 0.35 at one bridge for some reason. But that I only have two river runs to back up that data. Ammonia nitrogen levels average out to be a 0.05 milligrams per liter. And pesticides and fertilizers are also a contributor to algae. Now, yeah, here we go. We just added this slide, and this is the 0.05 is the average of all of those together. And actually, this is just for this year. Now, I'm afraid I can't give you data from 18 years ago, really, to compare to today. As you know, technology has skyrocketed past floppy disks. I can only tell you what we see, and that's a healthy ecosystem. Pollution levels for the most concerning contaminants are at or below detection most of the time. We see fish, animals, and people enjoying the White River, and we work daily to keep it that way. This next slide is a few of the resources that I've used to verify that data. If you're interested in this PowerPoint, I could send that to you. We decided to throw in a few slides about fishing because everybody had ideas on what they wanted to hear during these presentations. And our industrial compliance inspector, his name is Brian Donovan, he was an avid fisherman. And he just left us last month to pursue opportunities in Idaho where he could fly fish to his heart's content. So Josh, do you want to take over this little fishing section here?
All right. So these are some of the common fish that you'll find in the White River: bass, catfish, crappie, carp, bluegill. So if you do any fishing, I'm sure you've seen these. When you're going for bluegill, perch, or crappie, you can use a variety of different jigs with a bobber. Typically, the best is using live bait, so worms or minnows. The jigs themselves can be made of rubber or hair. The bobber will be to determine the lure depth, but these are more of the top feeders, so you don't want to go too low when you're setting these. When you're going for bass and walleye, you can use more artificial lures, soft bait, spinner baits, and these typically are more under the brush and the ledges, so you kind of cast towards that and kind of reel back. If you're going for catfish and carp, these are the bottom feeders. They're also the less likely to be affected by DO and stuff, so you can basically use anything on them and it'll bite. Live bait works the best, and you can use different methods of catching these fish.
If you have any questions about how much fish can be consumed from the White River, please see the Indiana State Department of Health Fish Consumption Advisory. And if you're wondering what more you can do, the answer is to do what you're doing. Conduct regular cleanups. Don't let the public forget about the river, its history or its importance to the community. You know, recruit and mentor a new generation of White River watchers and pretty much keep fighting for the river. And most importantly, get on the river. Use the White River and all its resources.